Thank you for coming today. As you see, I'm going to be talking about the good, the bad, and the ugly of timeouts and retries. And I hope that you don't expect to see many more references to this fine movie, because this is going to be the only one. I thought it was a funny joke, but that's the only one. Keyboard it is. So, well, this is me, Farruco Sanjurjo. I have 15 plus years experience building different kinds of systems, and now I work at Contentful, which is your one-stop shop place if you want to create, manage, or compose content from different sources. And there I work on the data storage layer and other distributed systems. If you want to find me online, you can do that. You can do so on GitHub and Twitter under Matric. That's my handle there. But on Twitter, I'm barely active, so just focus on GitHub if you want to. So the agenda, as you can see, is a pretty small one. I have only 2 things for you today. The first one is, why should we care about timeouts and retries? And if you don't believe me, I will show you. So the takeaways that I want you to take home today are that with timeouts and retries, we can improve the availability of our systems. We can increase the throughput as well. And at least we can put some boundaries to the latency of our system. Before going any further, and I guess that everybody here knows what a timeout is and what a retry is, I want to take a few seconds to make sure that we are all on the same page, or at least communicate what I'm referring to. So by timeout, I will be referring to the elapsed time before we consider an action as failed. By retry, I will be referring to the fact that we are executing an action again, an action that failed, hoping that the next time is going to have a positive outcome. So I was telling you before that the first thing I want to talk to you about today is why we should care about timeouts and retries, and that's distributed systems. One of the things that define distributed systems is that you don't have any guarantees about how long calls are going to take. Sure, most of the times calls are gonna you're gonna get a reply pretty quickly. You're gonna get the response as soon as you have called, as soon as the other system has finished processing the request. However, that doesn't have to be always the case, right? It can be that the call that you're making is to a system that is already overloaded. So it's gonna take longer to process your request because it's going through a backlog of queue requests somewhere in the system. So it's gonna take longer than usual already. It might be that the network is delayed. Maybe it might be that the issue is the network, like messages are being dropped, they're being queued somewhere. So again, it's going to take longer for you to get the response that you were hoping for. Or there may be a partition. So even though you might reach to the system and the system is healthy, the responses from that system may never get back to you because there is a network partition. So what we usually do in these cases, we sprinkle timeouts and retries here and there to protect our systems and ourselves from these situations. And this is fine. I mean, this works most of the times. You don't have to spend much time thinking about it. You just pick a value for the timeout, pick a number of retries, and move on. And that's fine, again, most of the times. However, it can be that these very same things that we use to protect ourselves cause some unexpected things to happen. Can cause downtime, can cause outages. So it's important that we pay some attention when we're using these tools in our system. So at this point, maybe I have convinced all of you that we should use timeouts and retries, and when doing so, we should be careful with them. However, I think that some of you might say, "Who's this guy? Why do I have to ask him? I mean, I just met him." So instead, I'm gonna do a small simulation today. I'm gonna run a live system, which is it's going to be a very simple one, as you can see here. It's going to have 2 components. The first one is just going to proxy the calls to the second one, and the second one, all it's going to do is going to apply some latency to the calls, and that latency is going to change throughout the simulation through some configuration settings. But again, very simple, and I'm going to be using a tool to send the traffic, initially with 5 clients, as I will talk through the simulation. But simulating is not enough. I also want to show you what is going on. And to do so, I'm going to use these 4 golden signals from Google SRE. That's how they measure the health, or how they recommend that people measure the health of the system. And the signals are the following. First, we have traffic. So how much load is being offered to the system. Second one is errors, the rate of requests that fail. Third is latency, or how long it takes to service a request. And the last one is saturation, or how full is your service. This one is the trickiest one to measure. And if you go to the SRE book, they have a lengthy description of what saturation can mean. But for the purpose of the talk, I'm going to keep it simple. And I'm going to just focus on how many calls are in flight at a given point in time. So what is the level of concurrency on this toy system that I was showing you before? Before going any further, I want to take a moment to talk about the diagrams I'm going to be using. On these ones, I'm going to be representing the interactions from the client with the system from the perspective of the client. So the client is going to make a call to the first component. The first component is going to forward that to the second component, wait for a response, and then after that, forward that the result to the client. And the client is going to be blocked until it gets the response from the first component. So it's kind of, you can think of a sequential system. The client depends on the response that it gets from the previous call before making another one. So that's why we have these other calls only after it got the first call. To keep things a bit simpler and more easier to visualize here on the slides, I'm going to remove in many of the diagrams this second component and also that first and second labels, just to keep things a bit tidier. When necessary, we'll add those. Okay, so now with the interesting things. This is the first of 5 simulations. And in this one, what I'm going to do is show you a system that is running already. It doesn't have timeouts or retries. And I'm going to introduce some change in the latency. I'm going to make that 1% of the calls are going to take 15 seconds. It means that of every 100 calls, 99 are going to be pretty fast. So the client calls the first component, the first calls the second, and it returns almost immediately. But then the 100th call is going to take 15 seconds. So before going further, I'm going to actually do the changes. This is the configuration file to make these changes easy for me during the talk. So here I'm setting the percentage of slowdown request to 1%. And now I'm going to show you this chart on Grafana. So this is running live. It's a couple of containers. And as you can see, we will immediately see the impact of adding that 15 seconds delay to 1% of the traffic. So the latency on the first component is already going up. I mean, this is the P99, but still already going up. The same for the second component. We're already at 3 seconds. Saturation, or the amount of in-flight requests, has gone up for both components. And the other thing is that the load that we are offering to the system has synced, has gone from around 300 to, and at this point, it's going to go further, but to not spend too much time, I'm going to move on to the slides. And what I'm going to do is I'm going to analyze some of these signals. So the first one is traffic. And as I was saying, I mean, if I left the charts running, we would get to this point where the system kind of stabilizes at around 80 calls per second from 300 that I was doing before. Why is that? Before we introduced these slow calls, every client was able to make around 50 calls per second. So every second, every client was able to send all this traffic. But now that we have these slow calls, every 100 calls, we have this slowdown. Every client is going to be blocked for 15 seconds, waiting for a response from the system. That means that for 15 seconds, they are not sending any more traffic to the system. And you can pretty quickly see the reason for that drop in traffic. The other thing was the saturation. As I mentioned, the second component went from almost having no in-flight calls to having 5, and okay. as I was saying, the second component went from having almost no in-flight calls to having 5, and the first component went from 3 to 5. So it was less exaggerated, but still noticeable. What is going on here? At some point, all the clients are gonna be stuck with one of these slow calls. So if we were to draw one vertical line across all of them, you could see that all these in-flight calls are happening at the same time on the system. So let's move on to the second simulation. Now in this case, I'm gonna modify the first component so that it times out after 200 milliseconds and see what happens. I'm gonna modify the configuration again. I'm gonna show you. You can see here that the changes are being picked up by the container. And we wait, as before, a few seconds, we will see the impact of making that change. So remember, now the first component is timing out. It's timing out after 200 milliseconds. Okay, something unexpected is happening. This thing here shouldn't be happening now at this point. Let me check the configuration. If I make no. Okay, let's move on. Let's see. But the important thing is that the overload has recovered almost to the previous level. Latency has gone down to close to those 200 milliseconds that we set as a timeout. But the other component is still stuck on those 15 seconds slow calls. So as we just saw, the first component before was stuck, waiting for the calls. Now it's timing out after 200 milliseconds. So let's analyze why we saw this recovery in overload that we saw on the charts. Before we had a timeout, as I explained before, the clients are blocked for 15 seconds waiting for the calls to complete before they are able to send more fast calls to the system. Now that we have a timeout, the first component is going to time out after 200 milliseconds, and immediately after, the client is able to send more traffic again to the system. And this translates into having this increase or this recovery in the overload to the system. The other thing that we saw actually wasn't such a surprise, is that the saturation increased on the system. We went from having 5 concurrent calls on both the first component and the second one to having around 50 on the second one. And this is kind of unexpected because we didn't change anything else than just the timeout. And the reason for that is that now that the first component calls the second one, and the second one is gonna take 15 seconds to complete, the first one is gonna time out, the client is able to make another call. And that call is gonna be running concurrently with the previous call that is still running on the second component. And because this is gonna be a fast call, gonna complete quickly, the client is able to make another call and then another one up until the point where the first call on the second component has finished, and then we stop having all these in-flight or overlap in the system. And the same happens to every other client running on the system. So it's not particular to one client, this happens to all of them. And if we were to have this span here was to be our monitoring window, and we're looking at the system at that point in time, we could see that we have 8 concurrent calls running on the system. And even though 8 concurrent calls might seem like a little thing, and on this case it's a little thing, it doesn't really matter because it's a toy. Imagine if you have a large-scale system where you have thousands of clients sending traffic concurrently. The effect of this overlapping can be significant because bound to every one of these calls are resources. You have sockets, you might have file descriptors, you have memory definitely. There may be contention on some matrix that you have somewhere, semaphores. So it's something that can have a significant impact on your system. So let's move on to the next simulation. In this case, we're gonna change the first component so that it retries once. So after every timeout, the first component is gonna try to recover by retrying once. That means that we're going to have a timeout, we're going to apply some backoff, and then do the retry. Okay, that means modifying this here. And let's see what happens on the system. Something I forgot to say before is that now that we have timeout, we start having errors. This yellow line here corresponds to 500s coming from the system. So it's the price we are paying for having timeouts. Some of the calls are failing. But now we introduce retries. So one of the things that we will start seeing is that there are no more 500s. So all the traffic is succeeding. But also the overload to the system has gone down compared to what we were seeing before. Saturation slightly changed, slightly trending downwards, and also an increase in the latency of the first component. This increase in latency is due to the backoff time that I was showing you before. So it makes a call, it waits a little bit, so that fails, waits a little bit, 1 second more or less, and then tries again. That's why we have this P99 latency here. But let's go into details on some of these charts. So the first one I mentioned was this drop in this decrease in traffic, the decrease in overload from the to the client, to the system. And the reason is that if we look at how the system behaved before having a retry, every time that we had a timeout, the first component would return immediately to the client, and the client was able to start making calls again until it was stuck on another slow call, which would time out again. But the key thing is that there was no timeout. No wait time. They were able to make calls as soon as there was a timeout. But now that we have a retry, the first component is going to apply the backoff and the retry. And that's going to delay the moment that the client can send another call again to the system. So that's why we're seeing that decrease in overload of traffic that the system is receiving. So to recap, timeouts, they allow you to abort early, free resources, which is a very important thing to keep in mind when building highly available systems. And at least it gives you the chance to bound latency. So your system is not depending on how other systems are behaving to put some boundaries on how long it's going to take a call for them to a call on their end. And then retries, they allow us to hide transient issues. By doing so, we are trading off availability for latency. So as we saw here, right? As we saw here, we got rid of the 500s, but the latency has increased because we are paying the price of the backoff and the second attempt on the retry to hide this transient issue. So it's something that you have to keep in mind as well when using retries. So let's make things a bit more interesting. And to do so, I'm going to make some changes to how the latency is calculated on the second component. So if you remember this component here, the only thing that was doing is that 1% of the calls are going to have a 15 seconds delay. What I'm going to do now is going to remove that. So no more 15 seconds delay for 1% of the traffic. Instead, I'm going to increase the baseline latency. So now every call is going to take at least 50 milliseconds. And then I'm going to make it so that the latency is directly driven by the concurrency of the system. And I think that this picture is going to show it much better. So as we increase the concurrency in the system, the latency is going to increase, in this case, exponentially. And this is not a far-fetched example because in many cases that's how systems might behave in real life. As soon as you start putting more concurrency in the system, the latency will increase. So before going on with the fourth simulation, I'm going to make those changes. So that means setting this back to 0, setting this to true to use the new feature, and that should be about it. And that when those changes by themselves won't have any significant impact besides reducing the latency on the second component. Now it's still stuck on those 15 seconds as the P99, but now we should start dropping because we're not having that problem anymore. Now it's thinking. Okay, so if I go back to slides, yeah, what I'm going to do is I'm going to increase the number of clients. Now I was using 5 clients, so I had 5 clients sending traffic to the system. What I'm going to do is I'm going to go to 5, 15, and then 20 and see what happens. So, by the way, I'm using K6 to simulate load in a very simple way. But if you were wondering how I was doing it, I'm using K6. So let's here increasing the number of clients to 10. You can see here 10 clients, and that will also show up here on the charts. So for example, I zoom into this chart, you can see that the saturation on the first component has gone from 5 to 10. The saturation on the second one is more or less the same as it was before, but that's because I increased the number of clients. We have now 10 clients sending traffic concurrently to the system. But beyond that, the overload has also, or the traffic has also decreased because we have more clients, and then the latency is going to increase. And because the latency is going to increase, then clients have to wait longer to make the next call. That's why the traffic has gone down. But for example, the latency on the second component, it's still pretty low, nothing to do with the value that we had before. So let's continue increasing the number of clients. So now we have 15. And we go back to Grafana. We'll see in a moment that reflected on the chart. So here, I'm assuming here again, you can see that we have around 15 calls running in parallel on the first component. It has increased slightly on the second one, but still nothing spectacular. The rest of the charts are more or less following the same trend. And now let's make things interesting and go to 20 clients. Again, we have to wait a little bit. And yeah, that wasn't such a great idea. The saturation on the second component is going through the roof. I don't know what the hell is going on here. There is no more successful work being done. All the requests are failing. Latency on the first component, on the second component has been increasing, and now it's going to be trending up all the way to 10 seconds, and that's because I have a limit. Else it would have gone through the roof. So what is going on here? What is the reason that going from 15 clients to 20 has caused the system to basically be, it's not down, but it's as if it was down because it's not doing any useful work. So yeah, this is, I think, the most interesting part of the charts. We went from having 15 in-flight calls to having 280, even though we have only 20 clients. So what is going on here? To explain this, I have to first introduce 2 ideas or 2 concepts. The first one is that as we get closer to having 20 concurrent calls, we start getting closer to the 1 second mark. And that's kind of a dangerous zone for us, as we will see in a moment. The second part is that the client I'm using is going to apply a 1 second backoff by default. So the first time it retries one failed call, it's going to wait just 1 second. And that's the default configuration on the HTTP client I'm using. So when we had less than 20 in-flight calls, the call on the second system might be slow, but it's going to take less than 1 second. And even though the first component is timing out, going to apply some backoff, and that backoff would be, as I said, 1 second. So the 200 milliseconds timeout plus the 1 second backoff adds to 1.2 seconds. And that may be enough so that the retry executes without overlapping with the previous call on the second component. However, once we are at 20 concurrent calls or more, we're already over 1 second of latency on the second component. That means that that call on the second component is going to take more than 1 second. And what before was enough, so that 1.2 seconds, which was enough before to avoid overlap here, chances are that it's not going to be enough. So every time that this happens and we retry, we're going to add a call that is going to overlap with the previous call. So we're going to be adding more load into the system ourselves. So if we zoom out a little bit, I'm going to show you the same, but with a little bit more perspective. When we have more than 20 clients and we're retrying once, this is what happens. The call to the second component is a slow one, so it's taking more than timeout. The first component times out, applies some backoff, retries, but that was right. But the retry is overlapping again, so that times out. The client sends another call, but that's already overlapping with what was running already. Times out, applies some backoff, retry, overlaps, and this happens with any client. So you can already get an idea of what is going on and why the system is totally getting out of control. Because what we have here is a self-reinforcing loop. The more load we have more timeouts. And the more timeouts we have more retries. And because we're retrying more, we are adding more load. And because we're adding more load, we're timing out more. And this goes nonstop. So we have a system that is feeding into its own demise. It's basically bringing itself down. I mean, as we saw before, it's not fully down, but it's not doing any useful work. So for the purpose of availability, it's as if we took it off from the network. Okay, so maybe 20 clients is too much for this toy system that I built for this talk. Let's go back to 5 and continue with the talk because this is a bit useful. So I'm going to set it to 5. As you can see here, we went from 20 to 5 clients sending traffic to our system. And if we were to switch to Grafana, okay, it seems that, I mean, at least the first component went back to 5. That's good. We're still not getting any 200s out of the system. But the second component, even though it has gone down a little bit, it's still stuck here around 75 in-flight calls. But we have reduced the number of clients to 5. So what is going on? Because again, even though I have reduced the load that I am offering to the system is as good as if it wasn't there, because there is no 200 coming out. So why is that? This is a hieroglyph. Anybody has an idea what I'm trying to say? Okay. This is a hieroglyph for a metastable failure. Metastable. Amazing joke. So metastable failures is the title, or metastable failures in distributed systems is the title of a paper that was released a few years ago. And this is the result of a research from some people that were looking at how how large distributed systems fail. And they noticed that there were some patterns to it. Sometimes they fail because you have bugs. Sometimes they fail because you have configuration issues or machines go down. But other times you have these metastable failures. And what they say is that these metastable failures have caused widespread outages at large internet companies, lasting from minutes to hours. Paradoxically, the root cause of these failures is often features that improve the efficiency or reliability of the system. So timeouts and retries, anyone? they also said that metastable failures occur in open systems with an uncontrolled source of load, where a trigger causes the system to enter a bad state that persists even if the trigger is removed. So just as we saw, we had a trigger that brought the system to a very bad state where it wasn't able to do any useful work. And I tried to fix that by going back to the previous state, like removing that trigger, and the system didn't fully recover. It was still kind of, from the customer perspective, it was still down. This is a diagram from the paper as well, and I think it illustrates pretty well what's going on here. So we had a system that was working fine, it was stable. But as we started increasing the concurrency and increasing the load, we started approaching that 20 concurrent calls in the system, and also getting closer on the 1 second latency, which for this system in particular is the vulnerable zone. And when we were there, and I make the change to bring the number of clients to 20, I entered this metastable state, which is what I showed you before. We have this self-reinforcing loop where the system is feeding into its own destruction, so to say. And then, yeah, there is this beautiful fat line to recovery. But as the authors of the paper said, there are usually only two ways to get out of this issue, of this situation. One is to drastically remove load. So if you're getting, I don't know, 1,000 calls per second, maybe you have to rate limit or drain until you only have 10 calls per second. Or the other option is to shut it down and bring it back up again to clean the system from this bad state setup. And you also have to be careful when bringing it up again, because if you were to switch it off and switch it on immediately, you will end up in the same space. So what you have to do in these cases is to switch off, switch on, and then increase the traffic gradually to prevent the system from crashing immediately after. So what I'm gonna do is that I'm gonna stop everything here. I'm gonna bring it up again. And I'm gonna do one thing. I'm gonna retry more than once. So up until now, the first component was retrying only once. So what would happen if the first component would retry once, so apply some backoff once, retry, that fails, some backoff, retry again, that fails again, wait, and retry. So 3 retries in the context of 1 client call. So what would happen? Let's see. For that, I'm gonna change 3. So this is the system. By this change, nothing's gonna, so going to 3 retries, nothing's gonna change on Grafana now, but it's just gonna show you that after rebooting it, we are back to where we started. So the system is behaving in a same way. We have again 200s. The saturation has gone back again to 5 concurrent calls. So everything is good again. So I'm gonna set again the number of clients to 20 and see, by making this change, I have make my system more available. So as usual, we have to wait a little bit, but we already see here that the first component has increased its concurrency to 20, and the second one is behaving more or less. We don't see anymore that massive spike in concurrency that we were seeing before, and we're still able then to do some useful work. The system is managing. The system is not totally useful. Some side effects of having these 3 timeouts are that the latency on the first component has increased because we are applying more 3 times backoff wait times. But yeah, as I said, the system is available, which is what matters in these cases. So why is that? Well, this is what I was just telling you, that the concurrency has increased on the first component, but this one it's under control. So why is that? Some issues with the slides, but the thing here is that once call from the first component times out, because the second component is taking longer than the timeout period, the first component is gonna apply some backoff, it's gonna retry, and maybe this call actually overlaps again. But the second time it applies backoff, it's gonna be longer because it's gonna be an exponential backoff. So you want to wait longer. And it retries. And maybe that retry again overlaps. So you know what? We apply some backoff again and we retry. But this time we were lucky enough we waited long enough so that that last retry didn't overlap with the previous call. And if the same happens with all the other clients on the system, we are able to break that self-reinforcing loop that we had before. So that's all about the simulation. There's not going to be more switching back and forth between Grafana and slides. And before wrapping up, I want to tell you a few things about retries. Always back off. Like never, 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 never retry immediately after a failure. Because if the reason for the failure is that the other system is overloaded, by retrying immediately, you are just making its life more miserable. You are not giving it time to recover. So you should always back off, and it should always be with an exponential waiting time and some jitter. And the reason for having an exponential wait time is that the more times you retry and the more times you keep failing, it means that the other system is still struggling. So you should wait every time that you want to retry, you should wait longer to give more time to the other system to breathe and to recover from the issues that is having. And the reason for the jitter is that if you, let's say that you have, 1,000 clients sending traffic to you, and they all the calls that you are making as a response to their calls are failing. They're failing because the other system is overloaded. If you were to retry all those calls after applying backoff, if you were to retry all those calls at the same time, you would end up having what is called a thundering herd. You will have these 1,000 retries happening at the very same point in time. And if your system was somehow recovering, you are just pushing his head down into the floor again. So by using jitter, you are in this random value, random waiting time, so that you spread over time the moment when the retry happens. So always back off and always use exponential wait time and jitter. Not every error should be retried. If the reason for the error is that the payload is malformed, the client sent the wrong authentication key, just by retrying is not going to solve the issue. You are only adding useless load to the system if you retry every error by default. So you have to be mindful of what errors you are going to be retrying. And the last thing is that you should think of how your system is structured and consider retrying only on the closest layer. And this is better seen with an example. So let's say that we have this setup we have 3 services, A, B, and C. And we're going to retry on each layer. That means that when A calls B, B is going to call C, and C is overloaded. So every call from B to C is going to fail. On that case, we're going to have 4 calls from B to C. The first call plus the 3 retries. Because all the calls fail, B is going to return an error to A, which is going to retry on its own. So you're going to have again the same situation. A calls B, B calls C, all that fails. Long story short, C is going to receive 12 calls because of this setup. However, if we retry only on the closest layer, what happens is that A calls B, B calls C, all the calls fail, but on this case, C is going to be called only 4 times instead of the 12 that we had on that setup. What we have to do here is we have to organize our system or design our system such that B returns to A, hey, there was an error, but please don't retry. This situation is not retryable, to prevent this multiplication of retries, which again, on this example might sound like a small thing going from 12 to 4, But imagine if you have a system which is getting thousands of calls per second. It can be the reason for service C never, ever recovering. So in conclusion, use timeouts and retries. They are here to help. They are very useful tools, but don't discover in production how your system behaves. I know that this is the hardest thing to do because all the things, many of the things that I show you, they are difficult to capture in unit tests and integration tests. These are behaviors that only manifest under load when you have your system running in production. So again, tricky thing to do, but that's why you have things like chaos engineering, or you can do some load testing in-house where you simulate scenarios to exercise these paths that are usually not triggered because things behave correctly and things are fine. And you don't want to be in a situation where you have to debug this in the middle of the night when something starts paging. And that brings me to the last point, that observability is a must. You cannot run a distributed system without knowing what is going on. Imagine that if I try to explain to you today all the behaviors of this tiny system without having these 4 signals available, it would have been impossible. So you have to make sure that you have the tools that you need to understand how your system is behaving. Else you would be totally lost. And that brings us to the end, almost on time. If you want to know more, that first link there takes you to a gist with 10 or 12 articles or documents about timeouts, retries, cascading failures, things that are pretty much related to what I have been talking to you about today. And yeah, the other one is if you want to stay in touch. We have time for questions, and I have a mic here. If anybody, okay, I can pass it somehow. There you go. I don't know if it's working or not.
Is it better?
Yeah.
Thank you. So obviously you can load test the whole system, but it can become expensive given you have a lot. Is it possible to have some sort of formula that you can project how your system behaves given that you know those 4 pillars? Like, can you calculate how your system would behave given that you know how many retries you can apply, what kind of timeouts you have, what kind of latency you expect from your system?
I mean, that's something I have never used, but there is this universal scalability law, and it's pretty mathematical, pretty interesting, but that gives you an idea of where the bottlenecks on your system might be. Like, sometimes we think that by adding more machines to the system, for example, we might be better off because we have more machines, right? But that's actually, there is always a bottleneck somewhere in the system, and the amount of work that you can parallelize until there is a choke point, because then you have to synchronize. That's what this universal scalability law is going to tell you. For what I have been talking about today, I cannot think of any mathematical formula that is gonna help. The thing is, is if you were able to characterize if you were able to characterize how your system behaves under load, and you were able to come up with some sort of chart like this, that might be a good approximation for you to tell, okay, as I increase, and you can do this maybe like in a local setup. You can run some local tests, and that might give you some idea how your system is going to behave when you have it running on production. But again, I don't know of any formula that you can apply out of the box for this kind of things, because every system might have bottlenecks in different places. It will behave differently under load. Some systems might have bottlenecks on I/O. Others might have some data structures that they have to protect with some matrix or semaphore, and that might be the bottleneck. So it really depends on how the system is designed.